Good afternoon, dear masters. Let me first introduce myself. My name is Maria Chernysheva. I'm also an associate professor from the division of radiochemistry. And here is my contact email. So if you will have any questions, please feel free to send me an email. And today I was asked to discuss with you one of the important field of radiochemistry concerning with labeled compounds and radio tracer method. And since you have already heard some lectures concerning with nuclear medicine and application of radio-labeled drugs as a diagnostics or therapeutic agents, you understand that radio-labeled compounds have a very huge application in different fields, including chemistry, biology, and medicine. And the first question, let's consider what is radio tracer, what is labeled compounds, and probably I will tell you how can we also use it, not only as nuclear medicine, not only in nuclear medicine. So first, let's define method of radioactive tracer, which used labeled compounds. A foreign substance mixed with or attached to a given substance to enable the distribution or location of the latter to be determined subsequently. And there are several types of tracers which are used. The first type, a physical tracer, is one of is attached physically to the object being traced. The second type is chemical tracer, is a chemical with properties which are very similar to those of substance being traced, which with which it's mixed homogeneously. So it's chemical tracer is just a mixture of labeled and non-labeled compounds. And an isotopic tracer is a unique isotope, either radioactive or sometimes stable isotope of the element to be traced. And finally, the final group is radioactive tracer, is a physical or chemical tracer having radioactivity as its distinguished property, which allows detection at small concentration and hence after large transport distance. This all definition are taken from UPAC, so you can use it where you want. And let's consider an isotopic tracer more exactly. It's a tracer which only differs in isotopic composition from the substance to be traced. And the first question when we discussed labeled compounds or radioactive tracer is how to give name and how to write a formula. In other words, the first topic is concerned with nomenclature of radioanalytical chemistry. And labeled molecules are usually subdivided into two large groups. Isotope labeled compound is a chemical substance in which part of molecules are labeled with an isotope so that observation of isotopic composition make it possible to follow the compound or its fragment through physical, chemical or biological process. And if we have only labeled compound, in other words, without tracer, it's another part of the slide, such compound is called isotopically substituted compounds. And in the other words, you can also call them carrier-free. So in this compound there is no non-labeled materials. The first question concerning with labeled compounds is how to write a structure and how to give a name. The isotopically substituted compounds, the symbol for isotope may be placed in the structural formula as it written in the examples, and if we want to give a name, we should put it into the round brackets immediately before the name of the compound. And here are some examples. For example, C14 labeled methane, and in the name, which is written below, the position of isotope is identified in the round brackets. And in this case, since we know the direct position, we also should put it in the round bracket. For example, 1 C14 labeled acetic acid or 2 C14 acetic acid. And I want to put your attention on the correct, on the left side of the slide, and incorrect names of formulas, of labeled compounds. Here you can see an isotope is given in the last position in the correct written. When such a compound is mixed with a corresponding compound which is non-labeled, which don't have radio or radioisotope, such mixture is called isotopically labeled compound. That can be also identified by formulas and its name. And the difference is that the isotope is placed to the square brackets before the name of the compound or within the formula. And here again are some examples. Ethanol, which is labeled with oxygen 18, can be written like first part, and the same is formula. And again, if we know the position of radioisotope, we should also give it in the square bracket like 2 oxygen 18 labeled glycolic acid, as a second example. And there are several types of isotopically labeled compounds, which are listed here in the table. They include specifically labeled compounds, selectively labeled or nominally labeled, non-selectively labeled compound, uniformly labeled, generally labeled, and final is isotopically deficient. Now let's consider each group separately and find the difference between all of them. The first group is specifically labeled tracers, and according to the UPAC definition, it's a tracer in which the label is presented in a specified position. In the other words, an isotopically labeled compound is designed as specifically labeled when a unique isotopically substituted compound is formally added to the analogues isotopically non-labeled, in such case both position and number of each labeling nuclides are defined. And in this table we can find that if labeled methane is added to non-labeled methane, it gives rise to specifically labeled compound. And here are examples with carbon 13 and tritium labeled organic molecule. I want to emphasize that although the formula for specifically labeled compounds doesn't represent the composition of the bulk material, which usually consists of the specifically non-modified compound, and does indicate the presence of the compound of chief interest, the isotopically substituted compound. So again, it's a mixture of isotopically substituted and isotopically non-modified compound. The next group is selectively labeled compound, or in modern UPAC rules, this compound is called nominally labeled. It's a tracer in which label is present mainly in a specified position, according to UPAC definition. Another topically labeled compound is distinguished as specifically labeled when a mixture of isotopically substituted compounds is formally added to the analogues isotopically non-modified compounds in such a way that its position or positions, but not necessarily the number of each labeling nuclides, is defined. A selectively labeled compound may be considered as a mixture of specifically labeled compounds. And let me then give you, about how to write a formula. A selectively labeled compound cannot be described by a unique formula. Therefore, it's represented by inserting the nuclide symbols, presented necessary locant, but without multiplied subscripts or any other positions, in a square brackets directly before the usual formula, or if necessary before part of the formula. And I also will show you an example. Here is on the right part of the slide how can we write the formula of selectively labeled compound. And this formula, in which radioisotope, here is tritium, is put in a square box, and we don't know how much tritium in it and in which position it is. We know that it's mixed with non-labeled methane. We're also known that it's a mixture of a methane that contain one, 2, 3, or 4 tritium atoms is its structure, or 2 or more of such labeled molecules. And we know also that it's mixed with non-labeled methane, and so we should address such mixture to selectively labeled compound. And the name of selectively labeled compound is formed in the same way as the name of specifically labeled compound, except that the multiplying subscripts following the atomic symbol are generally omitted. And the other group is non-selectively labeled tracers. It's a group of labeled compounds. An isotopically labeled compound is designed as non-selectively labeled when the position and the number of labeling nuclides are both undefined. And so non-selectively labeling is indicated in the formula by increasing the nuclide symbol enclosed in square brackets directly before the usual line formula with no locant or subscript. And here is an example of carbon-13 labeled butyric acid. It's formula on this part of slide, and the name of the non-selectively labeled compound is formed in the same way as the name of selectively labeled compound, but contains neither locant nor subscript in a nuclide descriptor. The next group is a uniformly labeled tracer, and according to UPAC definition, the tracer in which the label is uniformly distributed over its possible position is called uniformly labeled tracer. And when we want to write a formula, we should put a symbol U describing a labeled compound in which the label is distributed in the statistically uniform or mainly uniform manner between all its possible positions in the molecule. Propionic acid is, in my opinion, very good example. And if we have a propionic acid which is defined with the symbol U, it means that we have a mixture of equimolar amount of the molecules that contain label in first, second, and third position. And so we and also in such mixture we have non-labeled propionic acid, and so such mixture is called uniformly labeled tracer or uniformly labeled compound. The other group is of labeled materials, of labeled tracers, is generally labeled tracer. According to UPAC definition, a tracer in which the position of the label is not defined. This definition is usually applicable to high molecular weight materials. Here is example with protein, which is labeled with tritium. And to identify the generally labeled compound, generally labeled tracer, we should put a symbol G in the square brackets. And so we describe the labeled molecule in such way, indicating that in this material we have tritium label, but we don't know its position, and we also have non-labeled molecules. And the last group is isotopically deficient tracer. It's a very interesting group, but in my opinion, it's not usually used in chemical experiments. In this group, to these groups belongs compounds in which isotopical composition is differ from its natural, and an isotopically labeled compound may be designed as isotopically deficient when the isotopic content of one or more element has been depleted. In the other words, when one or more nuclide is present in less than natural ratio. And to identify such group of labeled compounds, we should add symbol def directly before isotope we want to, which is given in the amount that is less than natural ratio. And here is example for chloroform, which is deficient in the content of carbon 14, and here you can see def carbon 14 and then the total formula. The name of an isotopically deficient compound may be formed by adding the symbol def immediately presenting without hyphen and also to the name of the molecule, again def C14 chloroform, which is written directly here. And so now we considered all types of labeled materials which can be which you can find in literature, and now you know how to identify it. And I want to emphasize that if you have square boxes, square brackets, you should understand that this material contain labeled compound, and it's a mixture of labeled compound and non-labeled compound. And if you see round brackets, you should understand that this material don't have molecules which are non-labeled. So you should understand. You should understand that sometimes you can identify the position, or you cannot identify the position, or you can identify the amount of labeled material in the mixture, or also you cannot do it. And in most cases, for nuclear medicine, for example, you want to have a compound which have high specific radioactivity and no carrier. I believe it's clear for you from your previous lecture, but sometimes in, for example, analysis of drug behavior in biological experiments and in chemical experiments, you deal with compounds that contain radioactive material as well as non-radioactive. But since the properties of labeled compounds and non-labeled compounds are similar, you can trace the behavior, the distribution, for example, of drug in different systems, including biological one. So if it is clear, let's consider methods of preparation or production of labeled compounds. And again, there are several classes and several groups of methods that can be used for preparation labeled materials. The first group is chemical synthesis. And the other group is isotope exchange. Biosynthesis is also used for preparation of labeled molecules. And there are two non-usual for chemists groups of preparation of labeled materials, which are nuclear chemical methods that used either hot fission or method of recoil atoms, and beta decay of labeled compound. And the last group is physical chemical methods, which includes photolysis, chemical accelerators and discharge, and radiation chemical synthesis. So let's consider how we can synthesize the labeled compound. And I want to emphasize first, when we start the discussion, that radiochemistry is usually deal with very small amount of the material. So volumes are usually less than 1 milliliters. And in some cases, and in most cases, the chemical synthesis is provided automatically, and in particular for preparation of labeled materials for nuclear medicine, the whole synthesis is provided automatically, and chemist is just control the process by computer and then provide an analysis of the final product. So there are some requirements which for radiochemical synthesis. The first one is radionuclides are usually obtained in simple chemical form. For example, simple substance, oxide or salt. So the task of radiochemistry is to develop a simple and effective method for converting a radionuclide into the required chemical form. So the first requirement for radiochemical synthesis is if we have a multi-stage synthesis of our compound, it's required to obtain that the label should be introduced, if possible, at the last stage, both from viewpoint of radiation safety and for economic reason. You understand that the yield of all chemical reaction is never 100%. So if we introduce radioactive label, for example, on the first step, and if we have several steps, like let's say 3, in all stages we will lose radioactivity. And you know that labeled compound is usually significantly difficult to obtain if we lose it, and so from the economic reason we will also lose the material, which is not very cheap, let's say so. And the other requirements is when synthesizing compounds with high specific radioactivity, it's necessary to use small amount of reagent. in fact, we are talking about micro synthesis, which required special equipment and methods of work. I just told you that in most cases the synthesis is provided automatically, so why I written here that we need a special equipment. And you should understand that if the procedure is developed for huge amounts of the reagents, it sometimes cannot be used for providing microsynthesis. And when working with large radioactivity, special safety measures are also required. So we should provide dose control in our laboratory, and we should keep in mind that some rules from the radiation safety to provide both synthesis and analysis of labeled compound safely for the chemist. And finally, sometimes it's necessary to take into account the effect of ionizing radiation on the course of the reaction. For example, radiolysis of starting compounds and reaction products. So we should keep in mind that we deal with radioactive material. It means that the decay goes every moment, and ionizing radiation can influence on our starting materials, on our starting molecules, and as well on our final product. Sometimes the syntheses have a very small yield because of radiolysis of initial materials, and we should care about how to keep our labeled compound if we need it, for example, for future synthesis, to avoid radiolysis process, because our labeled compound have a label, radioactive label, and so ionizing radiation should be kept in mind. And let's consider the method that I have already listed more carefully, and I will show you some example of preparation of labeled compounds, not only for nuclear medicine but also for chemical and biochemical experiments. The first example that I want to show you, it's a synthesis of such molecule, synthesis of stereospecifically tritiated cholesterol. It was published in 1978. This science, he is very famous chemist who used tritium and I have a citation from his words. He used tritium and deuterium for labeling different organic materials, and he studied some biological processes used these labeled compounds. For deuterium, he used mass spec for analysis the distribution of deuterium in his other words, but other studies, and directly from this study he analyzed how such cholesterol molecule is transformed to that one, in its reorganization in plants. So he synthesized cholesterol that contain tritium in known position, and for this purpose he used chemical reaction, in particular sodium borate tritate and lithium alumitritate in the next reaction, and sodium boron tritate also in the last reaction. And as you can see, for the first two syntheses, he introduced label, as we just mentioned on the last stage, and unfortunately here it was a requirement for the synthesis. The label was introduced in the alpha position, so on the first step, and the yield, I want to emphasize that the yield of such reaction was smaller than for that one. And then, let me going back, and then he analyzed the distribution of label in the final product. And so he was first who find the mechanism of such transformation, and he published his result in labeled compound in pharmaceutical journal. So here is an example of chemical synthesis, and you understand that we can use isotope containing materials for introduction radio label by an ordinary chemical synthesis. Another interesting group of methods of preparation of labeled compounds is an isotope exchange. So according to UPAC definition, an isotope exchange is the exchange of places between isotopes of atoms in different chemical or physical states or positions. So isotope exchange is a chemical reaction in which reactant and product chemical species are chemically identical but have different isotopic composition. In such a reaction, the isotope distribution tends toward equilibrium, and as a result of transfer of isotopically different atoms or groups. So let me see, yes, I have an example of isotope exchange, and since you have seen from the definition given here, we have a reaction in which one component have, for example, a radioactive label, and one component have the same element but another isotope. So under the certain conditions, sometimes in the certain conditions, or and sometimes spontaneously, such molecules will be changed by a nuclide, and so such system finally will come to the equilibrium in which the isotope is distributed in all possible positions uniformly. So let's consider the mechanisms of isotope exchange reaction. The whole variety of mechanisms can be divided into two large groups. One mechanism includes only electronic transport or redox reaction, which proceed quickly and with low activation energy. Here is an example how isotopes of plutonium in the different oxidation form, or isotopes of technetium 99 M and technetium 99 both in form of pertechnetate, can be subjected to isotope exchange, and finally we will find significant amount pertechnetate in the oxidation state -2 and pertechnetate with technetium 99, as well as plutonium 239 in the oxidation state +3 can be subjected to isotope exchange reaction with plutonium 238 in the oxidation state +4, and in the equilibria we will have plutonium 238 in the oxidation state +3 and plutonium 239 in the oxidation state +4. So it's just a redox reaction which includes radioisotopes in the different oxidation states. And the other mechanism that is used for synthesis of biological molecules, for example, include the mechanisms with the transfer of ions, atoms, or group of atoms. The exchange of isotopes in the later case can proceed by dissociative mechanism or associative mechanism. So the first reaction is an example of iodine introduction into the organic molecule. I mean the organic molecule that contain iodine, which is not radioactive. Let's say it's stable isotopes, and if we want to introduce radioactive label, let's say we have iodine 123 in a gas form. So first we should obtain iodine in form of atoms, and then it will substitute iodine in the initial iodine organic iodine contained iodine organic molecule, and the final reaction, which is carried out by associative mechanism, includes introduction of iodine ions into the aquatic system, and in final product we will obtain iodine molecules that contain radioactive label. So these reactions can be successfully used for introduction of radioisotopes in the different molecules, including organic molecules, and for sometimes it's used for analysis of the reaction mechanisms and so on. Another interesting method, which is used for preparation of in most cases biologically important labeled compounds, is biosynthesis. These groups of method includes transformation of radioactive substance into more complex compound in living organisms. It can be carried out in vivo or by means of enzymatic reactions. In the other words, biosynthesis can be carried out in vitro. And here is an example that I have found. It's a preparation of labeled fructose from carbon-14 labeled glucose. And here you can see the reaction. This synthesis is carried out in vitro by means of enzymatic reaction. And these groups of methods are widely used if we need a compound which with a direct content of labeled in the final product. And this method have several advantages compared with synthesis, in ordinary chemical synthesis and anisotopic exchange. The huge advantage is the possibility of obtaining biological active compound in required enantiomeric and enantiomeric form. So, since enzymatic reaction is usually carried out on the specific mechanism, and a final product will have specifically an enantiomeric form. So sometimes it's critically important for biosynthesis and future application of the labeled product. And the other advantage is no restrictions on the complexity of the chemical structure. You know that sometimes it's quite different to synthesize, for example, biomolecule that have required properties, that have required for structure and no chemically, let's say, labeled byproducts. And so in this case, biosynthesis is very important and very useful. Unfortunately, it also have disadvantages because of high radiation. The first one is high radiation sensitivity. I just told you then in the chemical synthesis we should keep in mind possible radiolysis of the initial molecules and the final product. And in this case, enzymatic activity of an enzyme is usually very sensitive for radiation. So we cannot use very high radioactivity. We cannot introduce high radioactivity into the synthesis, and as a result, the second disadvantage, we cannot obtain the compound with high specific radioactivity because of sensitivity of the initial material, of initial enzyme or cells to ionizing radiation. And the last disadvantage, the need to isolate the target product from complex mixture of compound. Yes, in biosynthesis we usually deal with macromolecules or biologically active molecules which have very similar, let's say, size, properties, and so on, physical characteristics of initial product and final products. And finally we have a mixture that contains initial product and here is written target product, and the complex mixture of the compounds. So I think that these techniques, except probably isotopic exchange, is clearly for chemists, like chemical synthesis. I think you deal with chemical reactions, so chemical synthesis should be clearly for you, but again, keep in mind that the amount of the compound that we introduced into the reaction is much smaller than in ordinary chemical synthesis. And biosynthesis is also used in chemistry and biochemistry to prepare specific compounds. And if we used, as here, if we used the compound that contain radioactive label, for example, label fructose, after an enzymatic reaction, we can obtain carbon-14 label glucose. So then let's consider some specific nuclear chemical synthesis and the nuclear physical methods for introduction radioactive label into different molecule. And first I want to show you a rather famous method of introduction of tritium into organic molecules, which also can be identified as self-induced exchange reaction with tritium gas. Or this method is called after the science who first published it, who first provided such synthesis. It was Wildbach, and so the technique is called Wildbach method. The method is used for introduction of tritium into biomolecules, for example, biopolymers like proteins and sugars. If we put organic molecule into the ampoule which is filled with tritium gas and keep it for a long time, as I remember, Wilbach keep it for, here is written for several weeks, but it's better to keep it for several months to give a chance tritium to decay. Finally, we will find that organic molecule contain tritium label in any possible position. Why it goes? So you know that no, excuse me. Why it goes so? You know that tritium is a radioactive isotope of hydrogen, and it possesses beta decay with rather low energy, and its half-life is approximately 12.3 years. And after tritium atom is subjected to beta minus decay, it forms helium-3, isotope of helium. And so such molecule that have helium and tritium is not stable. So helium is leaves the molecule with an electron, and so we obtain a very reactive species as tritium in cation form. So such cations interact with organic molecule, And so tritium is introduced into the biomolecule. So this technique, Wilsbach method, is widely used for introduction of tritium labeled into the different molecules, which cannot be labeled, for example, by chemical synthesis or biosynthesis. And on the basis of the same property of the formation of cations, nowadays we have a direction in radiochemistry of obtaining or preparation of different compounds and some new organic molecules can be obtained by the methods which is very similar to Wilsbach technique. Here is an example of nuclear chemical methods of generation of nucleogenic phenylcations, and they are used in an ordinary organic synthesis. On the first step, tritium is introduced into the benzyl, and on the first step we obtain benzyl which is labeled with tritium. It's very good if we have 6 tritium atoms in the molecule, but in most cases 2 tritium molecules is enough for preparation of phenylcations. After that, what is written here, such benzyl molecule is subjected to the decay of tritium with emission of beta minus particle and the formation of helium-3. And after that, when helium-3 leave this complex, let's say complex, and we obtain phenylcations that is very sensitive for presentation of any anions in the system. So such cation can interact with it with formation of different organic molecules. And here I have an example of preparation of different molecules from phenylcations and such organic compound. And so on the finally we can see different organic molecules which can be obtained by different mechanisms. And I want to emphasize that this technique allowed to obtain new organic molecules which cannot be synthesized by means of an ordinary organic synthesis. And Professor Shepina, whose publications and doctoral thesis I have just cited, she was first who developed this direction in radiochemistry, and I know that she obtained in 2020 a molecule which was new, and only in probably last year or in previous year such molecules, such compounds was synthesized by means of an ordinary organic synthesis. So these two procedures, which have the same, the very close mechanism, let's say, which use the decay process of tritium, can be successfully used for introduction of radioactive label into the different compounds. And on the previous slides, you have seen the nuclear chemical procedures for introduction of radioactive label into the organic molecules. And now I want to consider the last group of physical chemical methods that can be used for introduction of radioactive label into the different molecules. And I want to show you an example of physical chemical method which is called tritium thermal activation technique or tritium thermal activation method. This technique is based on Langmuir hydrogen dissociation into atoms. And when Irving Langmuir studied the behavior of hydrogen at low gas pressure and in the presence of tungsten catalysis, he found that under the temperatures close to between 2000 and 3000 kelvins, he found that hydrogen can form atoms. And I believe you know that hydrogen atom is a very reactive species, and so it can interact with different targets. And if we used tritium or deuterium, it's the same thing, but tritium is radioactive. And you know that deuterium is also isotope of hydrogen, but it's also stable as a protium. If we use other isotopes of hydrogen, we also obtain its atoms on the surface of hot tungsten filament. And if such prepared tritium atoms interact with the organic target, which is placed on the walls of the reaction vessel, tritium atoms can substitute hydrogen in any possible position. You understand, it's a joke. In any possible position in the initial organic molecules. And so we will obtain labeled compound in which tritium is in unknown position, but it's very applicable for radio labeling of different organic molecules, from simple organic molecules like amino acids to huge organic macromolecules like proteins and sugars. So here is some physical characteristics of the reaction, and the activation energy of the first reaction of preparation of tritium atoms on the hot tungsten filament is approximately 2025 kilojoules, and the mechanism of the reaction is usually described by radical mechanisms. So first tritium atom substitute hydrogen in the target molecule with formation of organic radical, and then the next tritium atom interact with it radical with zero activation energy, and so we obtain a labeled compound. And as I told you, tritium atoms can substitute protium in any possible position. So we're we can see the competition of three most important reactions. So if the substitution occurs in CH bond, which is written here, we obtain labeled parent compound. So the compound we usually need. And if the substitution occurs in the functional group, we obtain tritium in the labile position. It's the arrow going down, and you can remember from my lecture, or you can understand it, that in such position tritium is not stable. I mean, not radioactively, but it's not stable, it's not chemically stable, and it can be easily exchanged back to protium in the for example, water solution. So the first step of purification of labeled compounds is purify the parent compound from tritium in the labile positions. And if the substitution, if the whole functional group is substituted with formation of radical like written here, what we obtain labeled byproduct. So if the reaction that I have written here and that I have shown you before is very simple, so just subject the organic molecule to the interaction with atomic tritium. The reaction is usually carried out just for several seconds, usually between 10 and 20 seconds, and then what we need to do, we should apply all possible analytical methods for analysis of labeled mixture to purify it from tritium in the labile position and labeled byproducts. And usually for this purpose, dialysis for macromolecules and size exclusion chromatography is used, and for small molecules like amino acids, what we can do, we can dissolve our labeled compound in water, for example, and then evaporate it for several times for isotopic exchange reaction between protium and tritium in the labile position, to make sure that all labile tritium is moved from the labeled compound. And after that, when we finished with labile tritium, we should purify it from labeled byproducts. And as I told you, for macromolecules, size exclusion chromatography is usually used, and for small molecules, other types of chromatography like HPLC, ion exchange chromatography, and TLC, thin layer chromatography, is also used for purification, because, as I have already mentioned, and I will repeat it again, then in radiochemical synthesis we have very small amount. For example, this target that I call target is just portions of milligrams. So in the final product we have just let's say a few milligrams of labeled compounds. So what we can do, we can use analytical columns and thin layer chromatography as a purification methods, not only for analytical runs. This is one of significant peculiarity of labeling techniques of radiochemical synthesis. That in sometimes we used analytical methods for purifications, not only for analysis. Here is a short list that shows you the different compounds that can be labeled with tritium by means of tritium thermal activation technique. It's applicable for biological macromolecules, it's applicable for lysozyme as a protein, and it's applicable for rather small molecules like dodecyl sulfate and dodecyl 3-methyl ammonium bromides, which are very useful surfactants, surface active materials, which are used in different physical chemical fields and biochemistry. And moreover, this technique is applicable for biomolecules with unknown structure and unknown chemical composition, like humic substances. And as you can see from this table, the specific activity that can be obtained by tritium thermal activation technique is rather high. Moreover, there is a techniques which allowed to introduce tritium with a uniform distribution of the label between different components of humic substances. So the yield of the reaction depends on different parameters like temperature on tungsten filament, the gas pressure, the amount of compound that we used in the reaction. So we can verify it and found the condition for radio labeling of different compounds. And finally, this method is applicable to introduce radio label into the carbon-based materials, including carbon-based nanomaterials. Here is example with nanodiamonds. And I also know examples with radio labels of carbon nanotubes, multi-volt and single-volt nanotubes. If the compound or if the material contain hydrogen, even in the trace amount, like carbon nanotubes, it's contain hydrogen in a very small amount. We can subject it for radio labeling by means of tritium thermal activation method and obtain a radioactive product with the same physical and chemical characteristics as an initial materials, but it will contain a radioactive label, and we can use this material to trace its behavior in different systems, including biological systems, if we want to analyze the biodistribution of labeled compound in animal or any living object. So I think I have a few minutes to show how can we use tritium labeled compounds, because I want to focus on today on tritium labeled compounds to make differ between lectures that you have before. I usually show application of labeled molecules in PET, but I know that you have separate courses, separate lectures on nuclear medicine, on nuclear diagnostics, and I believe you know about PET diagnostics, which used biomolecules which labeled with PET beta plus emitters, which are used in PET diagnostics. So since I have mentioned several methods of tritium introduction, and if I cite Lockley, who said that biosynthesis is very complicated, but tritium make it simplifier. So I want to show you some examples of application of tritium labeled compounds. The first is it's a physical chemical characteristics of different materials on its hydrophobicity. You know that hydrophobicity is one of the important characteristic of a molecule or solid material before its application in biological, for example, systems. Here we used tritium labeled nanodiamonds for analysis its distribution in the system of two immiscible liquids, and we used octane, xylene, and octanol as an organic system. And you know that the distribution in water octanol system is characteristics of hydrophobicity. And so we can see that free nanodiamonds and nanodiamonds which are modified with organic polymer. Here is an example with pluronic. It's three-block copolymer of ethylene oxide, propylene oxide, ethylene oxide, and it's surface active, and it can be easily put on the surface of nanodiamond. If we have labeled nanodiamond, we can find its low concentration in the bulk of organic phase, and so we can calculate from the radioactivity of an aqueous phase and organic phase the distribution ratio. And as you can see, the distribution ratio is very small for free nanodiamonds and modified nanodiamonds, but using a radioactive trace we can determine such small amounts. And the other example, again with tritium labeled nanodiamonds, is its analysis of its distribution in wheat seedlings. Nanodiamond is a material which nowadays is used in technical oils, and sometimes, and so it's can be found in the natural systems. And so it's very interesting how nanoparticles interact with plants, for example. Since we have, and unfortunately, there is no exact techniques to find organic molecules on the background of other organic materials, for example, in the plant. And if we have a radioactive tracer and its novel property as radioactivity, for nanodiamonds it's novel, we can put into the interaction wheat seedlings and tritium labeled nanodiamonds with rather high specific activity for providing autoradiography. And after a few days of the interaction, the wheat seedlings were dried and were analyzed to visualize the distribution, we provide an after radiography, and here is a photo of upper part and roots, and here is an outer radiography image from which we can see that nanodiamond can be absorbed on the roots, and some amount of it goes to an apical part, and then the material, the plant, was dissolved in the nitric acid, and the radioactivity of the solution was measured. So we determined the direct amount, since we know the initial specific radioactivity, and we can determine the amount of labeled material in different parts. Here is an example with leaves. And I also have a few more images with, again, the interaction after radiography of the result of the interaction of nanodiamonds with plants. And here in these experiments we used initial nanodiamonds which have positively charged surface, and the other sample was subjected for oxidation, and it have negatively charged surface, and then both these stuffs were labeled with tritium, and then put again into the experiment with plants. And what we can see that both positively charged and negatively charged nanodiamonds can be absorbed on the surface of the root. It can be transferred in the upper parts with high accumulation in the bottom, and moreover, both of them can penetrate leaves, and significant amount of nanoparticles can be found in apical part of the leaf. So from these experiments we can conclude that nanoparticles have the distribution, not only absorption on the plant surface, but it also can be uptaken and accumulated in upper parts of the plants, and such conclusions should be taken into account when we want to apply nanoparticles in different fields. Since nanodiamond is an interesting object, I want to show you two more results. Now with interaction, we have seen the interaction with plant, and now what's going on if nanodiamonds interact with cancer cells. Nowadays there are some publications which shows us that nanodiamonds can be used as a carrier in drug delivery. The first question is toxicity, and what we can see from this picture, that free nanodiamond and even a nanodiamond which is modified with drug which is rather toxic, red points show its the toxicity of free drug, and green points shows the toxicity, very small toxicity of the drug which is bound to nanodiamond surface. And if we have labeled nanodiamond, labeled drug, and labeled complex in which the label is accumulated in nanodiamond or in a drug molecule, we can follow the behavior of the complex as a whole. So here is the result of binding with cancer cells, and we can conclude that complex of drug with nanodiamond and nanodiamond itself have significantly high binding efficiency with cancer cells. So we can conclude since we have an initial part of the graph which is not coming from zero, we can conclude that this complex absorbs on the surface of cancer cell. We can suggest that it penetrates the cancer cell, and so we can conclude that the binding efficiency is rather high. So such type of drug carrier probably can be used in the development of drug delivery system. So what I want to say in I think it was the last slide. On this lecture I tried to show you that labeled materials and radio tracer technique is a very useful method for analysis or trace the behavior of the compound in different systems in vitro experiment that I have shown here, and in vivo experiments, and so I think on the next term we will have a special course with for you with concerning with labeled compounds and radio tracer techniques. So thank you very much for your attention, and if you have any questions, please feel free to send me an email. Thank you very much.